So welcome to another episode from Spiral Physics Education. So I'm going to be looking at practical skills in this episode, and we're going to be focusing on the vocabulary used when we're doing practical work. So we're going to be looking at independent variables, dependent variables, validity and fair test, control variables, reliability and accuracy. We're looking at those because they come up a great deal when we're doing practical work, and you could be asked about all of those and their meanings and all of those when we're planning practical work. So let's start with looking at independent variables. So generally when scientists are planning a practical, they really want to answer a question. They're thinking, how will this variable affect another variable? And those two blanks there represents the dependent and independent variables. So when we're trying to do this, for example, it could be that they might be thinking, how might voltage be affected if I increase the current in a circuit, for example. We've got two variables there, and it's important that you're able to identify which one's the dependent and which one's the independent. So when we're thinking about independent variables are the ones that the scientists choose to change. And that's very, very important to realise. That's the one that they are going to enforce a change on and monitor. So when we're talking about dependent variables, dependent variables are affected by the independent variables. So the dependent variables change because of the changes that the scientists have made. So if you like, the dependent variables depend on the independent variable. So there's a lot of dependent and independent going on there, but it's useful for you to try and to look at a few practical headings and questions to see if you can identify which ones would be the independent, which ones would be the dependent variables. So we've got three different investigations here, and what we're going to do is we're going to try and identify which one's independent and dependent in these. So we've got, how does mass of an object affect its acceleration? What happens to the bounce height of the ball if I drop it from different heights? And also, if I change the potential difference across a filament lamp, how does the current in the circuit change? So we've got three different questions. So I want you to just have a look at each of those and see if you can identify in each of those statements which variables are independent and which ones are dependent. So let's have a look at that first one. How does mass of an object affect acceleration? So how does the mass? So that means the scientist is going to change the mass. That's the independent variable. So we're looking at mass being changed by the scientist, and they're going to hope that the mass is going to change the acceleration. So acceleration depends on mass. So if we look at the next one, then change it around a little bit. There, we're looking at the bounce height depending on the drop height. So if the bounce height depends on something else, the bounce height is the dependent variable. And with the last one, with the filament lamp, the current depends on the voltage there. So and he says in there, if I change the potential difference, that clearly means that that's going to be the independent variable. So if the scientist changes it, it's the independent, and if it is changed by the independent variable, that means it's the dependent variable. Try and learn those two definitions. So let's have a look at validity and fair test. Now, whenever we do a practical investigation, it's got to be valid, and if it's valid, it's a fair test. But don't use the term fair test as a blanket statement. Examiners don't like it. So, for instance, you might say, why have they kept this as a control variable? You can't say to make it a fair test. You have to explain your understanding of that. So hopefully this bit will help you understand. So to make an experiment valid and therefore fair, what we've got to do is consider all the possible variables that might affect our outcome. And once we've considered all the other variables that may change our dependent variable, we try and control them the best that we can. Some aren't controllable, like room temperature is not controllable. That might change and fluctuate during a practical. But the best to our abilities, we try and control all of our variables. And that means that we have control variables. So the implementation of control variables make a practical valid. And what that really means is if we control all our other variables, because we've only changed one variable, we are confident that that one variable has caused the outcome. Okay, let's have a look at reliability now. So with reliability, we always try to make practicals reliable as possible. And what we try to think about that with reliability is reliability means repeatability. You're doing it again, aren't you? Just sit there. Just sit there. It means repeatability. So what that means is if someone has done a practical and they've got a result, it's reliable if some other person did the same practical and got a similar or the same result again, and that means it's reliable. So whenever we're trying to improve the reliability of something, we try to repeat it. So that's the real definition of reliability. So whenever we're doing an experiment, your teachers will often say, make sure that you repeat it. So if you repeat it and calculate an average, it gives you an opportunity to, yes, you're lovely. It gives you an opportunity to spot anomalies, do something about them, and to then calculate an average. So let's have a look at an example then. Well, let's say that a student is going to look at acceleration and mass. So in this experiment, the student's going to change the mass, and that makes the independent variable mass, and they're going to see if you're off them. Going to see how the acceleration is affected by that. So let's say their first set of results for 100 grams of these, and looking at them, they're quite similar, so I can't really spot any anomalies there. So I then add another 100 grams on, and I record my accelerations, and I look at those data and think, I don't particularly like that middle one. That one looks like an anomaly to me. It doesn't fit the same pattern. So when I do my calculations for the averages, I'm not going to include that 7.45 in my average. If I had time, what would be even better would be to repeat it again, so I had 3 pieces of data for my average. And that's a common exam question. What should the student do with that data? They should discount it. If they've got time, repeat it. But certainly when they're calculating the average, they shouldn't include it in the averages. So let's have a look at accuracy. And the thing is with accuracy, when we're ever doing an experiment, we very, very rarely know if our outcomes are accurate. We hope they are. But we only know if something is accurate if we know what the answer should be. And that doesn't always happen in physics. Your teacher, when they do practical work with you, they might know what the answer should be, so they can tell you if your answer is accurate, but really you won't know until you're told what the outcome should be. So let's give you an example of this. Let's say that a student is looking to calculate gravity, and they get an answer of 10 newtons per kilogram, and they approach the teacher and say, I've got 10 newtons per kilogram. And the teacher says, actually it's 9.81 newtons per kilogram. Now, they're not exactly the same, but because of uncertainties in measuring and using equipment, they're accurate. That's an accurate result. I'd be happy if a student got 10 newtons per kilogram when they should be getting 9.81. Let's have another example. Let's say a student is looking into resistors, and they get an answer of calculated at 349 ohms. And they go to the teacher and say, I've got 349 ohms. The teacher says, well done. However, it should be 3.5 ohms. They're nowhere near each other. So they're not accurate. And the teacher will look at it and go, actually, looks like you're a factor of 100 out. So there might be something wrong with the calculations there and be able to spot somewhere where they've gone wrong. But certainly the answer is not accurate. So what we try to do during a practical is adopt good practical techniques to hope that our answers are accurate. Let's have a look at reliability and accuracy. And you might have seen a lot of dartboards floating around, pictures of dartboards floating around in laboratories to try and help you with reliability and accuracy. So in this, I've adopted this process in a video so that you can see it. It's animated at work. So it's going to be a little bit dangerous because darts are going to fly across into the dartboard. So we're going to be aiming for the bullseye. Okay, so yes, got the bullseye. Whoa, got the bullseye again. Well, got the bullseye again. So here, that person over there, thanks, is both reliable and accurate. Okay, so let's try that again, shall we? So we're aiming for the bullseye again. Okay. Whoa, no. Whoa, no. Whoa, gosh, no. This time they're not reliable or accurate. They're just all over the place. Should we try that one again? Okay, throw at the bullseye. Whoa! And missed again. Oh, and missed again. However, this time they're reliably hitting 12, but they're still inaccurate. And finally, and whoa, whoa, and whoa. Not particularly accurate, but they are around the bullseye, but they're not particularly reliable. They're hitting different numbers, but their accuracy is improved as before. I hope you found that useful in learning a little bit about the vocabulary of practical work. Do subscribe to the channel so that you can improve your understanding of physics and hopefully boost your grades when you come to doing your exams. I'll see you next time on Spiral Physics Education. Thank you.